Yes. Okay. So let's give some hints about that. Good. Last time. So we saw Zaremba's conjecture. There's Zaremba's conjecture that there exists some A so that for all D, or maybe for all sufficiently large D, there exists a B co-prime to D, with B over D having all partial quotients, bounded by this number A, and maybe A is 5, or maybe A is 2, if you want every sufficiently large. I mean, that's Hensley's conjecture, so Zaremba and Hensley's refinement. And maybe I'll say even more about Hensley's conjecture. Equals 2. Certainly not A equals 1. If A equals 1, then it's all ones, and the only fractions are Fibonacci numbers, and then there's very few numbers. Okay. And then we let RA be the set of fractions B over D with this property. We let DA be the set of integers D, so that there exists a B co-prime to D and B over D in RA. And we saw that the number of elements of RA of n, so this is the number of fractions B over D in RA with D bounded by n, is, well, we discussed how this would be of order, roughly of exponential order n to the 2 delta. Delta is the Hausdorff dimension of the Cantor set, which is the set of limit points of these RA.
Which is less than 1, right? That would be...
Which is less than 1, yes. So delta is less than 1, and it's even for A equals 2, bigger than a half.
This is proven until now. Everything is proven.
Well, I didn't give all the details of this.
Yeah, but I'm saying it's there.
These are all theorems.
Yeah.
These are all theorems.
Apparently the Hausdorff dimension for the bigger A's, is it going to be like monotone increasing?
Yes.
Is the right? So
Yes.
they're always going to be bigger than a half.
Yes. In fact, Hensley even worked out, Hensley in 90, okay, don't quote me on these numbers. So here's the theorem of Hensley's, is that this dimension is actually 1 minus something that goes to 0. It goes to 0 at the rate 6 over pi squared, which you've seen already. So it's 1 minus 6 over pi squared 1 over A plus big O plus, let's just say, little o of 1 over A. So we know the rate at which this is going to 1 as A goes to infinity. At least to add to, he got more orders, but this is just crudely to first order. Okay. Now, what can we get immediately from this theorem? This is also Hensley's theorem.
Well, I guess kind of a peripheral question. What is it useful to know this asymptotic for delta A? Is it just like an out of curiosity, or can you get mileage out of something like this?
Well, so the first versions of our results will all depend. The stuff with Bourgain that I mentioned depends on delta A being close enough to 1. And the question of how close enough, well, the first thing we did an asymptotic approximation for what A should be for this. And then we had to go and do a separate calculation with that particular A to learn if the dimension actually is where we thought it was, in the range that we thought it was. So, so this is useful as a guess for how large you need to take A in order to find that particular dimension. And then from there, you go in and check that the dimension does indeed, the dimension of that particular, so our theorem was about A equals 50. And the way we saw the 50 was the dimension needed to be at least 0.99 or something. And that's how we guessed 50. And then you run the algorithms that determine the dimension on 50 and see that it's above 0.99. Right. That kind of argument. Okay, so it's useful, but it's useful in a sort of roundabout way. But anyway, just for your general knowledge. So what, and then DA, how many elements, what can we say about how many elements there are in D up to N, just from this information? There's already something we can say. So again, RA, my graph of things is like this. So here's D going up to capital N. And then the fractions are all here. So this is how I think of RA of N.
Okay, so RA is everything.
RA is all the fractions from 0 to 1. And then, but I plot them graded by the value of the denominator, D.
Right.
And so the question is, what's the,
Fiber?
what can we say? Yeah, so how big can each fiber be?
Right.
So this multiplicity, MA of D is the number of B less than D, co-prime to D, so that B over D is in RA. Right, this fiber.
Right.
This is the pre-image, this is the inverse image of iota of D, where iota maps RA to D, A sending a fraction B over D to D.
Yes, last time you set this up as a sum. Right, and then
When we counted RA of N, it
Right,
was a
that's
sum
okay,
over
okay.
the multiplicities. So what's a trivial bound for the multiplicity? Completely trivial. How many B's are there less than D?
in RA.
So in other words, drop this condition and drop even this condition. I just want something very crude.
Oh, okay.
D, okay? So the fiber above each guy is at most D. And we know that the sum is exactly as you just said, the sum of D up to N of these multiplicities is at most, is not just at most, but is N to the 2 delta to first order. And so if each of these is less than D, and their sum has to be N to this power, how many D's, what's the smallest number of D's that must be represented?
N to the 2 delta A minus 1.
Exactly, N to the 2 delta minus 1. So this is an immediate consequence. If I have fewer than this number of deltas,
Oh,
of
the
Ds.
average would dip too much.
and each of them contributes only at most N, then I don't get enough, I mean, minus little o1, to again, just to exponent order, then I don't have enough D's to make up this total sum. Because each D has a restricted amount of multiplicity that it can contribute. So again, this is the trade-off between very few D's having very large multiplicity, or is it the other way around? Is the multiplicity of this size and the number of D's is everybody? This is this universe 1, universe 2 discussion. I'm just reminding you of what we said. So this is kind of immediate. And notice this goes to 1 as A gets large. So without anything, we can get not quite a density, a positive density set, but a set that's approaching. So by making, so from this, by
DA was this fiber.
DA is how many D's actually occur. How many D's have non-zero fiber,
Oh, yeah, okay, yeah, sorry.
right? So I'm saying either the multiplicity is huge for very few D's, but at least this many D's, or, which is what we really think, the fibers are of size D to the 2 delta minus 1, and the number of D's occurring is everybody.
Okay, this makes a lot more sense, yeah.
Okay, so by making A large, and hence making delta close to 1, which implies delta A is close to 1, which implies 2 delta A minus 1 is close to 1, which implies 2 delta minus 1 is going to 1, right? If delta is 1, then this is 2 minus 1.
You get N.
You get the number of D's of size N is at least N to the 1 minus epsilon, right? For your favorite epsilon. Okay, so so we can create lots and lots of D's, but this is still very far from even a positive proportion.
Yeah, no, this is like, right. And does this line up with with the conjecture, right? N equals 5, you expect everything, so you very much expect this to happen.
Yes.
right? So,
Yes. But so we can get lots of them in an exponential sense, but we're very far from even a positive proportion. So positive proportion, even for A large, was not previously known before our work. Okay. So, and of course, the theorem, again, with Bourgain is there exists an A like 50 or, so my student Xinyi Huang worked this down to 5 based on work of Frolenkov and Kahn. Maybe I should add some of these names. So this is Frolenkov and Kahn, who did this, who sort of pushed our work from 50 down to 5 only for positive proportion, and then Xinyi Huang did what I'm about to say. There exists an A such that so that you get density 1. When you divide by n, what's the proportion of these guys? That goes to 1. Okay,
Right.
so not only is there a positive proportion, but that proportion is 1 when A equals 5.
Yeah, so what you're saying before is that we don't have any idea of what sort of constant you could even get or anything like that.
You mean just from this elementary considerations?
Yeah.
Right. Right. Not only can we not get a constant here, we can't get any positive proportion. We can get a lot of points by making A large, but we can't even come close to a positive proportion. So this does not only a positive proportion, but gets you density.
It says not only do we get more than, let's say, a billionth in proportion, you get them exactly line up a little bit. Right?
Yeah, the ratio is exactly 1. So density 1 set of numbers satisfied. All right. What can I say about the proof? All right, so let's sort of start the kind of key, and it's a trivial observation, but it turns out it's absolutely essential here, is the following. So if you have a fraction b over d that's equal to 1 over a1 plus 1 over a2 and so on down to 1 over al, that happens if and only if when you take the matrix a1 1 1 0 times a2 1 1 0 and so on down to al 1 1 0, that matrix product comes out to some db something something. And so let's make this a little exercise. It's very
The first thing you see when you see convergence, right? You see that in quality theory.
this relationship between the matrix multiplication and
Yeah.
which fractions.
Yeah.
Yeah. So what does this trivial observation give us? So what's the key object that we want to study? So the main object that we want to study is, so you take these matrices that look like this, and you're allowed to take any word in these matrices. Well, that's a semigroup. So we want the semigroup, so this means semigroup, no inverses, not generated as a group, but generated as a semigroup, over all the A's up to A. And let's call this gamma A.
Oh, okay. So this gives you an object to study.
It gives you an object to study. That object sits inside, so actually let's call this gamma 0 of A, because this is a subset of GL to Z. It's not a subgroup, it's a subset. Why GL2 and not SL2?
Well, I mean, the determinant's negative.
The determinant's negative of all the generators. So I'll immediately pass to let gamma A be gamma A0 intersect SL2. Which is even length words, even length
Right. Okay.
words
Yeah,
in
exactly.
gamma A0. And gamma A, if I want all of gamma A, that's just, I can put an initial letter or nothing. So I can put the identity I can put the identity, or I can put one of these, this finite list of 1, 1 up to A1. So it's an orbit. This is my way of saying it has finite index, but there's no such thing as index for semigroups.
So you're just like separating them into equivalence classes. Really.
Right, there's just all the even length words, and if it's not even, then I can prepend one of the generators and then multiply by something even.
Right.
And that gives me everything. Okay, so this is just,
Even isn't true.
so the point is that you lose nothing by passing to gamma A. In fact, you gain something, because if you recall, this expansion is not quite for a fraction, for a rational number. The continued fraction expansion is not quite unique,
Yeah.
because you can replace this, one.
AL minus 1 plus 1.
Yes, yes.
1 over 1. Yeah.
Unique, it is unique if I require L to be even, the length to be even. Because then you can't, if you change the last letter by subtracting 1 and adding
Only one is.
only 1 is even.
Is acceptable. Yeah.
So now we have this unique representation. And in fact, so here's another elementary exercise. There's a one-to-one correspondence now, one-to-one correspondence between these fractions and gamma. What's the correspondence? How do I get from a fraction with all partial quotients bounded by A with even length words? Well, you just do this.
Yeah.
So if you give me a fraction, I make this element. So if you give me a fraction, A1 through AL, and AL, these are all bounded, and L is even. L is 0 mod 2. Then I make the elements, well, this maps to the element A1, 110 up to AL, 110, which has even length, and so this will be in gamma A. How do I go the other way? Well, that's what this exercise was.
Right.
I get a dB. So I get a dB,
Reconstructed.
and I just take B over D. So in fact, if we really care about only these first columns, so what we really care about, not gamma A itself, but the first column. So the first column is gamma A times the column vector 1, 0.
Professor, I'm a little bit confused.
Yes.
So from RA to gamma A, it's fine, like, it's clear.
Yes,
The other way, it should be 1 to 1, right?
it should be 1 to 1.
But you claim that the stars do not matter.
That's right.
So somehow B and D should have fixed star.
So
They do fix star. Yeah.
So this group gamma A, what we're really getting to is that the group gamma A doesn't have any parabolic elements. I'll say that again in just a second. But yes, so the fact that this is unique, I mean, we have maps in both directions, and the maps commute, so it has to be unique, and that in fact tells you that that this
B and D will define star.
will uniquely determine star star. So this is uniquely determined.
I mean, we determine it once, so star is just including the algorithm, right?
Yes. Ask that question in just 1 second. Let me just finish writing what we really care about. So you see that this is the first columns. This thing. So this is this orbit O. That's what we really care about. Now to get right to your question, let's make another little exercise.
Yeah, determinant 1. Yeah, it has to be.
If I have a matrix DB, I don't know what to call this, alpha beta, has determinant 1, and DB, same DB but different, alpha prime, beta prime are in SL2Z. If these are two matrices with determinant 1, then they differ if then the first one, let's call this gamma 1, and this one's gamma 2, then gamma 1 is equal to gamma 2 times a parabolic element
Yeah, it shouldn't be too horrible to check.
for
You-
some n.
You get like a one parameter set of solutions to this thing being equal to one, and then they're all off by like just a
So,
simple multiple.
yep. Proof 1, I guess I'm solving the exercise for you. Proof 1 is exactly what you said, Chinese remainder theorem. Chinese remainder theorem. Proof 2 is, well, if that's what's supposed to happen, then let's compute gamma 2 inverse times gamma 1. Okay, in other words, I multiply by gamma 2 inverse on both sides. And then, well, gamma 1 is this dB alpha beta. Gamma 2 inverse is I flip the diagonal elements and I negate the off diagonal, negative b. And then when you multiply this out, I have negative bd plus bd, so I get a 0 here. And so, and then this has to be, this is going to capture the determinant, and then this is whatever it is. Okay, so again, I've done the exercise.
Not much nicer. Go faster.
So because this is uniquely determined, that means there are no parabolic elements. If there were any parabolic elements in this semigroup, then it would not be unique. Okay, so we really care about this orbit. Now this gamma A now is a subset of SL2Z. Gamma A is a subset of SL2Z. And I claim that this thing is thin. So this is sort of definition by example. My claim is that gamma A in SL2Z is thin. So what do I mean by thin? Let me give you the definition that appears. There are lots of versions of this for groups. The word thin is horribly abused, and it's a real shame that it's not a shame. It's a really good word for this. It's a shame that other people used it before us for different reasons. And but I'll give you the definition that appears in a paper of mine from a few years ago. It says the following: let S be some arbitrary subset of Z to some dimension. Okay, so some set of points, and of course you can generalize. Let's just stay over Q. So you have some subset of points. Let V be the Zariski closure of S. So what do I mean by this? You look at all polynomials. So F is a polynomial, let's say with complex coefficients, over the n variables.
The algebra geometry topology.
Yes, this is the Zariski. Yeah, I'm trying to do it without any. I'm trying to give you sort of the very
Abridged version.
the abridged version, the very hands-on version. So I want to look at the set of all polynomials so that f of s vanishes for all s in S. So I want the polynomials that vanish on all of these sets. Okay, in the intersection of these polynomials, in other words, I want the set of all points z so that f of z is equal to 0 for all f in this set. So you look at all polynomials that vanish on the set of all elements of S, and then you look at all points, if you like, over the complex numbers, but more abstractly, this is just a variety.
I see.
You look at all points that vanish on all polynomials that vanish on all the elements of S.
Okay. So that's going to include in particular these elements.
Yeah, I'll show you in a second how this, well, maybe let's do the example side by side. So for example, this gamma A, what is the set of all, if a polynomial, so I claim that the Zariski closure of gamma A is all of SL2. So what does that mean? i.e., if a polynomial vanishes on every element of gamma A, then that polynomial, what does it do to a matrix? It's determinant of the matrix -1 times an arbitrary polynomial. This is arbitrary. So let me say this again. If you have some polynomial in all the entries, in the 4 entries, gamma A I'm thinking of as a subset of Z4.
Oh, okay, so you're taking the matrices and sort of embedding them
Yep.
this way, right?
Okay, so the matrix is just a 4 tuple of integers, every one of these matrices. And if you have a polynomial that vanishes on all of the matrices in gamma of A, then I claim that that polynomial is factors through the determinant equals 1 condition. In other words, that polynomial is determinant minus 1 times. So let's look at the other direction. If you have a polynomial that is determinant minus 1 times an arbitrary polynomial, then of course every element of gamma vanishes on this polynomial. Right?
Every element of SL2 should vanish, right? Determinant of.
Yes, exactly. So that's what this means. What this means that the Zariski closure of gamma A is SL2 means that the only polynomial that vanishes on all of gamma is also, any polynomial that vanishes on all of gamma also vanishes on all of SL2. Because this is the defining characteristic of SL2.
But why would we guess that this means that the gamma A should be called thin?
So I haven't finished the definition.
Okay, because it means that it's big. I'm gonna call it thin. It's big, right?
It's big in an algebrogeometric sense. It's so V is S by definition is Zariski dense in its Zariski closure.
Yeah.
So it's big in this algebrogeometric sense. So let S be a subset, let V be its Zariski closure. Then S is thin. S is thin if and only if, here's a definition, some room. If and only if the number of elements in S in your favorite ball of radius X divided by the number of elements in this variety, V, with integer entries, intersect the ball of radius X, if that ratio goes to 0. So something is thin if, despite being dense in the algebrogeometric sense, it has density 0 in the Archimedean sense.
What's the picture?
The picture is, so let's look exactly at this example. We have gamma A. I claim that the Zariski closure of gamma A is SL2. Okay, so again, what that means is any polynomial that vanishes on gamma A also vanishes on all of SL2. But the polynomials that vanish on SL2 is exactly the ones that factor through determinant minus 1.
Like, I don't understand the bottom, what's the point of the bottom equation? Like, what are we saying with it?
This ratio?
Oh, no, I
or
mean,
this?
like, yeah, there.
This.
I still don't quite see it.
Okay, let's come back to that for just a second. And let me finish this
Sure.
part of the calculation. So how many elements do we have in gamma A in a ball of size X? So I want all the entries bounded by X, let's say. It doesn't matter if it's an L2, if it's a circle or a square, if it's an L2 or an L infinity norm up to constants, these ratios will all have the same properties. Here's our relationship. It's not hard to see that D will be the largest element. Should I make that an exercise? So, exercise for all gamma in gamma A, gamma 1, 1 is largest. Just because of the generator, it's true. Yeah. Yep.
Okay.
And so cutting off gamma A is the same as cutting off D. And by this 1-to-1 relation, that's the same as RA restricted to X. And so the number of elements, the number of elements will be the same, roughly speaking, will be the same as how many elements there are in A of X. And this is n to the 2 delta. As opposed to the number of elements in SL2Z in a ball of size X. How many elements are there in SL2Z in a ball of size X? Oh, n, this is X. Ah, we haven't done this. We haven't done this. I forgot. I'm sorry. Have we done this or not? How many elements are there? How many matrices? How many integer solutions are there? So this is the number of A, B, C, D, all at most x, with AD minus BC equals 1, you know, in absolute value or something. Integers. Okay, you can choose any A and any D, and then BC will be some divisor function. So, right, so there's n to the epsilon choices. So very crudely, you can see by elementary considerations that this is going to be x squared plus x squared to first order. We can count this much more precisely, for example, by the trace formula and by other techniques. But very roughly, the number of solutions to this equation is there's x to the 4 possible variables, and it's being cut out by a quadric. So the chance of this AD minus BC being equal to 1 is 1 over x squared. The number of values of AD minus BC, the size of AD minus BC is x squared. So that's the range of the possible values. And we want it to hit one particular value. So that'll happen 1 over x squared at a time. There's a total of x to the 4 possibilities. And the probability of this is 1 over x squared. And so that's another way to see that there's going to be x squared total points. And so what's this ratio? The bottom grows at the rate x squared, the top grows at the rate x to the 2 delta, and delta is less than 1. So the ratio goes to 0. So the number of elements in gamma A in a ball of size x divided by the number of elements in SL2Z in a ball of size x goes to 0.
It's almost like kind of narrowly. Like,
Because delta could be arbitrarily close to 1.
Right, yeah.
Yeah.
It just barely this happens.
Yeah.
I mean, it's still with the power growth, it's not barely, it's not low.
It's not log, but it could be log in other situations. There are
Yeah,
other
I'm just saying,
subgroups.
It's a power saving.
Here it's a
fast,
power
it's
saving.
fast, it's
Yeah.
fast, it's not that stuff.
Let me point out that this is not a very good definition. In the sense that how many points are there in a variety? How many integer points are there in a variety? This is we're very far from being able to answer that in most cases. It's only in these nice, homogeneous spaces that we have tools to estimate these things. What if the variety comes out to x cubed minus y cubed equals x cubed plus y cubed minus z cubed, or x to the 17 plus y to the 17 minus z to the 17, right? So the definition is not a great definition, but it actually in all of the examples that we care about, it will do what we want it to.
I mean, we know how to solve x to the 17 plus y to the 17 minus z to the 17 these days.
These days, yes, but we would like not to rely on, those. So what about x to the 17 plus y to the 17 minus 2 z to the 17? Right, so very slight variations on those things, and all of a sudden we're in big trouble for counting. Okay, we have faultings. Anyway. So counting points on varieties is hard. In our applications, these Zariski closures will all be things where we do know how to count points on the varieties, and then we can determine this ratio. Okay, so it's a useful definition for the applications that we have in mind, but as a general definition, it's not. Andre, let's go back to try and understand this. So again, I want to look at all polynomials that vanish on all elements of gamma A.
Okay, you just make our S is gamma A.
Yes.
Okay.
So I claim, so first of all, if whatever polynomial you have is AD minus BC minus 1 times any polynomial in ABCD, this is not the derivative. This is any f prime. That's supposed to be a prime. F prime sounds like derivative. F sub 1.
No, that's fine. But I'm just why should this relation hold? This is
Why is that the Zariski closure?
No, I just don't understand that line at all.
Okay.
Yes.
Okay. So let's look again. We want to look at all polynomials in 4 variables, A, B, C, D,
Vanish on all of
that vanish on all of gamma.
Okay.
So first of all, do you agree that if the polynomial is AD minus BC minus 1 times A to the 17 plus B to the 17 minus C to the 17? So I'm just putting an arbitrary polynomial here.
Okay.
Any polynomial like that will vanish on all of gamma.
Yeah, you know, SL2 is equal.
Because in particular, AD minus BC is equal to 1 for every element of gamma.
Polynomial F will vanish.
The polynomial F
But
will
it's gonna-
vanish.
It's like gonna vanish independently of anything else, right?
as long as it
As
has
long as
this
that factor is there.
factor there.
Okay, and then what's the relevance of this to?
Well, that's just the definition of the Zariski closure. I'm trying to explain what the Zariski closure is. You take all polynomials that vanish on all the elements of S. I claim they all look like this. And then you look at their intersection. In other words, you take the set of all points that vanish on all such polynomials. But the only polynomials that vanish on all such polynomials are the ones where, like, these will all have different vanishing sets. So it's a way of stripping away this arbitrary part
Oh, so this
and
is
getting down to the
also-
essence.
So this is your claim, right? That this is what's going to happen.
Yes,
And because this happens, then it coincides
with SL2,
right, because F1 can be literally anything.
right?
Okay. Okay, and when you say right big X, you mean,
When I write a ball of size X,
yeah, in this case, you mean like a ball centered at any vector,
centered at the origin
centered at the origin of any radius?
of radius X.
Of radius.
X is the radius, yeah. So in
Oh,
other words,
that's what you mean.
that's what I mean. Yeah, I want to count how many points there are with all the coordinates bounded by X. So this is an L infinity norm. And I mumbled that if you take an L2 norm, it's not going to change anything. It'll change the constants, but not the growth rates, not the exponents. And the exponents are what's responsible for this set being a zero proportion in an Archimedean sense. It's a zero proportion of SL2Z while being, in an algebra geometric sense, very thick.
What is the
Full.
algebra geometric sense?
In this sense, the Zariski density. So I take the Zariski closure of gamma A, that's this variety. So SL2 is the variety AD minus BC minus 1. That's the polynomial that cuts out that variety.
You're saying in the Zariski sense, you get everything? when taking
You
the
get
closure?
all of SL2.
But you're saying that in this other sense.
In an Archimedean sense, you get almost nothing. You get 0% of the matrices of SL2 in the sense of Archimedean density actually occur in gamma A, even though all polynomials that vanish on gamma A also vanish on all of SL2.
Oh, okay. So you wanted to look at something like this so that, right, so you'd be able to say different things, I guess.
That's the definition of thinness. How can you tell something is thin? The definition is you have some arbitrary subset, you look at its Zariski closure, and you look at the ratio of how many points there are in a ball of radius X in the set that you're interested in versus the integer points in the variety. One is obviously a subset of the other.
Integer points on the variety. So, and our variety in this case is
Is the Zariski closure.
the Zariski closure.
In this case, the variety is AD minus BC minus 1. That's the equation that's cut out by the
Okay, you're just
variety.
taking like integral solutions to it.
Yep, that's all of SL2Z
And then the top in our example was what again?
is gamma A. So I'm applying this with S equals gamma A.
And gamma A was that like
That's semigroup.
Semigroup.
Yeah.
We talked about, oh,
This one.
okay, so what this is saying is that out of all matrices in SL2Z.
Yes.
The ones in here are few.
Yes,
Oh, okay, that's what you're.
that's
Okay.
exactly what I'm trying to say.
Yeah.
You look at all matrices with even length words that are generated by this. So that'll be something in SL2Z. How many of those do you get in a ball of size X relative to how many you get in all of SL2Z size X?
Right. So
And I
it's a
claim there's
measure
zero
of fewness
proportion.
in
It's a very thin, yeah, that's why the word is thin.
Okay.
Okay. And in fact, when you look at these, I mean, it's basically the same picture as this picture. That you don't get, if I let A go to infinity, I would just get the entire rectangle. In other words, if I don't restrict the partial quotients of B over D, then I'm just plotting, you know, modulo the fact, okay, so for primes, I'll get everything, and for composites, I have to worry about B being co-prime to D. There's a small number of holes, but roughly, if you zoomed out, you wouldn't be able to tell the difference between that and a completely full-in rectangle.
If you
There'd be
let-
n squared points.
Mean if you let n become big, is what you're saying?
No, if I drop the
Oh,
restriction
right.
on the partial
And then you
quotients.
should fill everything.
Right.
Almost. Okay. Okay. And then these RAs in correspondence with.
With
the
gamma A,
The semi-algebra,
semigroup.
semigroup. Okay. Okay, so you just. Okay, like it's common in number theory, you turn this into a matrix. There's an algebraic kind of problem.
And you learn quite a few things. It seems like this is a trivial translation. What's the difference between working in RA and working in gamma A? You learn from this algebrogeometric perspective, you learn a number of things. So for example, should I do this now? Yeah, well, we're on it, so I'm not gonna be able to help myself. For example, a slight detour. I mean, this whole thing is a slight detour. Slight is a slight exaggeration. Slight detour. Hensley conjectured something even more. Hensley conjectured more. Hensley conjectured more. Instead of looking at RA, which is the set of all partial quotients with all the AJs bounded by A, he says, I'll call it curly A, be just some alphabet of allowed letters. And then you let R curly A be the set of all of these things with the AJs in the alphabet.
Right.
The conjecture if alpha is greater than 2 cardinality, then
No,
no.
that would be an interesting conjecture, but that he knew was wrong. Because what really matters is that the Hausdorff dimension of the Cantor set, this Cantor set, which is the set of limit points of RA, has to be at least a half.
Mhm.
If this is not at least a half,
Yeah, you cannot hope.
then the number of points, the number of points in counted with multiplicity would be right. This is n to the 2 delta plus little o1. All of these proofs go through in exactly the same way. It has nothing to do with the alphabet. So if there are fewer than n points when you count them with multiplicity, when you drop the multiplicity, there's no chance of having a positive proportion of these denominators. Okay, so Hensley conjectured, sorry.
Oh, when?
96, I want to say. Hensley conjectured that if delta A of this alphabet is bigger than a half, which is the case for 1 and 2,
Right.
but is not the case for 1 and 3, for example.
It's not the case for one.
Already if you allow the digits 1 and 3, but not 1 and 2, then this dimension drops below a half. Okay, if the dimension is greater than a half, then the number of denominators occurring in this set up to n, then every sufficiently large number, then let's call it like this, then dA contains every sufficiently large number.
And then, so what would you have to do to make this work excluding 2, like 1, 3, 4 or something? Or is it not even, do you need to include 2?
You do not necessarily need to include 2, and you do not necessarily need to include 1. There's a way to do this without including 1.
Oh boy.
So what we observed, so this is a little, I guess, lemma. So this conjecture is false.
This one is false.
This conjecture is false because for a p-adic sense, he was only worried about the Archimedean place. He needs to worry about all the places. So what immediately when Bourgain and I saw this, I immediately said this is false. Let's go find a counterexample. So what so here's a little lemma. Let A equal 2, 4, 6, 8, don't quote me on this. I think 10 is as far as I had to go.
Mm.
Then the dimension was something like 0.517. Okay, it's bigger than a half.
Yeah.
But dA, if you reduce mod 4, you only get, I think, 1, 2, and 3. Or 1, 2, and 4. I don't remember what it was. So there are local obstructions that are not just the obstruction at the prime infinity. If your alphabet is only allowed to be even numbers,
Oh, okay.
sorry.
I see.
sorry, what do I mean? 0, 0, 1, and 2. Yeah, that 4, same thing as 0. 0, 1, and 2.
So okay, I see what you're saying. So you don't get 3,
You never get 3 mod 4.
and so you can't contain every sufficiently large number.
Trivial.
Oh, okay.
Okay, so the conjecture has to be modified to say every sufficiently large admissible number
Oh boy.
should occur as long as the dimension is bigger than a half.
Is a local to global problem.
So this is another, that's exactly right. That's exactly right. So this is a local obstruction. Local obstruction to having every number be sufficiently,
Wait,
every
so
sufficiently
How
large.
did you
number.
guys modify the conjecture then?
So the new conjecture, okay, now you really, this is not where I wanted to go. I wanted to get in, because this is still storytelling. I want to actually prove something today, but I don't know if we'll get there. So given an alphabet A, we call a number D admissible if D is in the reduction of dA mod Q for all Q. If there are no local obstructions
For that denominator?
for that alphabet.
For that alphabet.
So every alphabet has some set of local obstructions. Now this looks like a really bad condition, right? Because this is, I want to know what I don't know what dA is. And now I'm saying I'm going to look at dA mod Q for all Q. This seems like impossible to check. But in fact, it's this algebraic geometry that will tell us that this is actually very easy to check. That's what the group condition will be. I'll explain that in a second. Given an A, we call D admissible if for every Q it's in this set. And then the conjecture, the modified conjecture.
Because in a sense, you're avoiding the situation above, is what you're saying.
Exactly. So we believe these, not just the prime at infinity, but if you take into account the prime at infinity and all the other ones, then you have a local global.
Prime infinity, you mean like the flat case?
The Archimedean. This is the Archimedean condition. This is saying that I have enough points in an Archimedean sense, but I also might be deficient at some prime or prime power. Okay, so the conjecture says if you have an alphabet, if this alphabet has dimension, Hausdorff dimension bigger than a half, then every sufficiently large, exactly, sufficiently large, admissible D actually occurs in the set of denominators. Okay, so that's the modification to Hensley's conjecture that is needed. And the only way we knew to look for this was from understanding this condition as something called strong approximation of Zariski of semi-simple groups. Let me say a little bit about what that is, since now you've pulled me into it.
And then I guess like the difficulty in this conjecture is, I mean, a lot of things, right? Which are the admissible things?
So that looks like a difficulty. This looks difficult, but actually is very easy. This
Finding
looks-
which ones are admissible, but then like going to the global sense is then what ends up being very hard.
it's well, it's hard to say when a conjecture is hard, because if someone comes along with an easy proof, then you go, oh, it wasn't hard after all. But it looks, for all as far as we can tell, very, very hard. Okay, so this looks difficult, but is not. So let me try to explain why not.
So then this would solve the local part?
Determining the local conditions, yeah, but what do I mean? Determining local conditions, determining these local conditions is in fact easy. What do I mean by that? So gamma A is some subset of SL2Z. And it's a Zariski dense subset of SL2. And it's Zariski dense. As we said, any polynomial that vanishes on all of A also vanishes on all of SL2 over any ring, but in particular over SL2Z.
This would be independent of the alphabet.
That's as long as the alphabet has at least 2 elements.
Okay, that's where we got here.
Yeah.
Independent of.
Yeah, it's Zariski dense as long as the number of elements is at least
It'd be
2.
kind of a bad alphabet to just have a.
If it's a
one
single letter, yeah, then it's like Fibonacci's,
Right.
right? And then all bets are off if you're not Zariski dense in SL2. That's like a single hyperbolic matrix. The group generated by a single hyperbolic matrix is not Zariski dense in SL2. It's Zariski closure is a torus. It's a complex torus. We won't come back to that. I have to stop getting sidetracked. I want to do the circle method. We're not even close to it yet. So what this means, now this is just a subset. It's not even a subgroup. If you had a subgroup of a Zariski dense group, then you would know, so there's something called strong approximation.
The sub-semigroup.
It's a sub-semigroup, but you'll see in a second that that doesn't matter. There's some tricks here. Strong approximation for Zariski dense semi-simple groups, Zariski dense subgroups. This is semi-simple, unlike GL2. Okay, so I'll make this. Yeah. Semi-simple means the product of simple groups. Zariski dense, a strong approximation of Zariski dense semi-simple groups.
In the same sense as algebra 1, simple groups.
Yeah.
Okay.
Zariski dense semi-simple arithmetic groups. So let's just stick to SL2. Let's make our lives a little easier. If I have a subgroup, if gamma is a subgroup of SL2Z, and I look at gamma mod P, of course, that's going to be a subgroup of SL2Z mod P. Strong approximation says for P sufficiently large, which can be determined by gamma, and gamma needs to be Zariski dense, and the Zariski closure of gamma is all of SL2. Strong approximation says for P sufficiently large, depending only on the information of gamma, this thing is not only, the gamma P is not only a subgroup of SL2, it's actually equal to all of SL2. So the reduction mod P is everything.
Okay, so what you're saying before, what was it you said before, that it could normally just say it's a subgroup, reduction mod P, but here you can just say it's everything. Is what
Right.
this strong approximation.
Strong approximation is that if you have a Zariski dense subgroup of a semi-simple group, then the reduction mod P will be the entire reduction mod P of the ambient variety.
This is because the polynomial somehow must be.
It's a type of Chinese remainder theorem, exactly, in these groups. Now, some more words. SL2 is semi-simple. GL2 is only reductive, not semi-simple.
Semi-simple mean?
It's a product of simple groups. What does
Oh,
reductive
yeah,
mean
okay.
when you mod out by the center?
Right, right, right.
It's a.
Yeah, sorry.
I just want to throw these words around so that you've heard them and then you'll go properly study this
And
subject.
reductive, you were saying?
Yeah, when you mod out by the center, you get semi-simple.
We just did this in Kip's theory of groups class.
Great, great. So let me just point out that strong approximation fails for reductive groups. Strong approximation is false for reductive groups. In the following very strong and very elementary sense. For example, if I take GL2Z itself, GL2Z is obviously a Zariski dense subgroup of GL2Z. Okay, and the Zariski closure of GL2 is GL2. GL2Z is GL2. The only polynomials that vanish on GL2Z vanish on anything that's, I mean, this is just complete triviality, right? What's the reduction of GL2Z mod 5? So you take all matrices, 2 by 2 matrices with determinant plus or minus 1, you reduce them mod 5. You will get all matrices in Z mod 5Z with determinant plus or minus 1. In other words, 1 or 4. Because that's what there was here. What is, compare to GL2 Z mod 5. What's GL2 Z mod 5?
It's determinant 1.
SL2 Z mod 5 is determinant 1.
Right here. Plus
GL2 is just invertible.
Oh, you're right. You're right. Yeah.
You're invertible if the determinant is invertible.
Anything.
Yeah. So this is all matrices. This is what I mean by if there's a center, then there's something trivial that prevents strong
You're
approximation.
missing equivalence classes there.
All matrices in Z mod 5Z with determinant in Z mod 5 cross, which is more than just plus or minus 1. Okay, so this is strictly a subset of this.
This is interesting. So this is somewhere where GL and versus SL is actually going to matter.
That's right. That's right. And that's one of the reasons I wanted to pass from all words in those
The even
matrices to the
ones.
even ones,
Oh,
so that I have access to, for example, this SL2 phenomenon.
Does this carry over to things in general? Do we usually want to work in some sort of SL, PSL because of something like this?
Yes. Yes, there's a lot of, it depends on what you're doing. Sometimes it's more convenient to work in GL, which we saw. Oh, we haven't done Heck operators. God. When we do Heck operators, we will see that it's more convenient to work in. Oh no, even when we did the Osawa decomposition, right? We used 1Y01.
Oh, yeah.
Sorry, we used this matrix Y001, which is in GL but not SL, versus root Y001 over root Y, which is in SL. So if you're in SL, you have to, it's a little bit more, you have to divide out by the determinant, divide out the whatever power of the determinant. Yeah, and introduce square roots, and it's a little messy. And so GL is sometimes convenient, but for lots of other reasons, you really want to pass to the semi-simple group if you can. Okay, so in the case of our gamma A, this is not a subgroup, it's only a subset. How can I apply strong approximation? Why? It's only, yeah, but is only a sub semigroup. It has a semigroup structure, but not a group structure of SL2Z. So why can I apply? Can strong approximation apply? Well, when you reduce gamma, what you care about is gamma A mod P, or mod anything, mod Q. This is a semigroup. But a semigroup, this is a sub-semigroup, semigroup of a finite group. Because?
Because any element has
Finite order.
Right.
You pick up inverses.
So it has inverse.
So it has inverses. So you pick up inverses for free. Pick up inverses for free. This is what, Fermat or something, or Euler. Or whatever, it's finite, right? So you multiply the element by itself, you get back to the identity at some point,
Right.
which means it has an inverse, which means you may as well, so this closure, this subgroup will be exactly the same as if you had taken the group generated by gamma A and reduced that mod Q. Because you have the inverses either way when you reduce mod Q, which means when you care about this problem, all you care about, so to understand gamma A mod Q only need to know the group generated by gamma A as a subgroup of SL2Z. But already for A equals, or let's make it in terms of alphabets. If the alphabet is equal to 1 and 2, in other words, if A is equal to 2, then this group is equal to SL2Z itself. When you add in the inverses of those matrices, so let's make this an exercise. This is a simple exercise. You actually get all of SL2. So of course, when you reduce a mod Q, you're going to get all of SL2Q. I went too fast. Let's do it again. Andre, take me back.
Okay. Is it with the sub? So why were you saying? I just didn't get why taking the subgroup. I mean, the group generated by gamma A. Why are we doing that again?
Okay, so I want to apply strong approximation. Strong approximation says if I have a subgroup of a semi-simple group that's Zariski dense, of an arithmetic guy, then when I reduce mod and ideal, I get the same thing for Q sufficiently large. When I reduce mod Q, I'm sitting inside a finite group.
Yes.
Which means when I take enough powers of that element, I get back to the identity. Which means if I take one less power, I get the inverse.
Yes.
And so whether this is a semigroup or not, I pick up inverses for free.
You pick up inverses where?
So I look at the reduction of gamma mod Q. The structure of gamma is only semigroup. I'm not allowed inverses. I only take words in the generators.
Oh, so what you're saying is that if you take words in gamma A to turn this into a group.
If I allow myself inverses, that won't change anything about the mod Q structure because the inverses are already there.
Mod Q.
Mod Q.
Oh, I see.
So I may as well just look at the full group. I may as well give myself inverses. Adding into the inverses and the Archimedean side doesn't change, doesn't add anything, doesn't give me any advantage when I reduce mod Q. I already have that mod Q.
So you're saying is that you can't take the inverse of an element and then have it end up be mapping somewhere different, mod Q.
Right.
Because you already had an inverse.
I already had the inverse, mod Q.
Right.
And inverses
okay.
are unique.
Right. Okay.
So I may as well look in the Archimedean sense, not at the semigroup, which is some weird thing, but at the group generated by the semigroup. Give me the inverses too.
On the other hand, wouldn't this make it a little harder to work with?
Well, it changes if I go back to the original problem being to understand RA or DA. If I give the group the inverses, I throw away all the structure.
Right.
I throw away the fact that it's this correlation. Where were we?
One-to-one, yeah.
This one-to-one, exactly. This one-to-one, if I allow inverse of these matrices, I ruin everything.
Right.
I no longer have a correlation to continued fractions in this modular multiplication question where we started. So I'm not allowed to do that for the problem. But if I want to understand the reduction mod Q, go ahead and throw in the inverses.
Oh, okay. So I see what you're saying.
And when you throw in the inverses, it's an easy exercise to take, even for 1 and 2, take the matrices that you get of even length, multiply them together, and you'll see you'll get your favorite generators of SL2Z.
Okay, so you're saying for the alphabet 1, 2, you're saying what is happening?
That the group generated by the semigroup
is everything.
is all of SL2Z,
Even for that small.
even for that small alphabet.
Oh, I see. So yes, in a sense, the semigroup was already like maximal in a sense.
So mod Q, the semigroup is going to be all of SL2Z mod Q. Okay. Now for this alphabet, the evens alphabet, so there was a chance that Hensley's conjecture would have been right. If you throw away 1 or you throw away 2 and the dimension automatically drops below a half, then Hensley would have been fine.
Right,
But it turns out you can drop one, and if you add enough even numbers,
raise it back up.
the dimension can get back to bigger than a half. It turns out, I mean, there was no reason for this to exist or not to exist. And it turns out it does exist,
And it gives us a local obstruction.
and it gives us a local obstruction. For all the other primes, you can check that the group generated by gamma A is all of SL2
Really?
Z mod Q.
Wow.
And for this is the only place where you get a restriction.
This type of lemma that disproves the field conjecture, can we extend it somehow? Because, I mean, according to what you said, one extended to conjecture, there exists a C such that if delta alpha is greater than C, then D of A contains all numbers but finitely many.
Yes,
So if I say C is not 1/2, but C is like 0.99,
yes,
can we tweak the counterexample so as to disprove what I said?
yes. And in fact, that is done in Xinyi Huang's thesis. So this student of mine,
So
she-
in other words, you can't rescue the conjecture with just delta A.
you can rescue the conjecture with just delta A by making delta A large enough.
That's what you're saying.
So he identified the maximal alphabets having local obstructions.
Oh, interesting. So what are the numbers that you get out of this?
So you take the infinite alphabet, 2, 4, 6, 8, 10, infinite alphabet, and he computes the dimension of this alphabet. And I don't remember what it is. It's 0.880 or something.
And this has an obstruction.
This has an obstruction. And there's another alphabet, which I think is like 1, 5, 9, 13, and so on. It's something like this.
Interesting.
And it turns out that this is also has some dimension 0.60. And these-
The max of those two, then
Yep.
you-
Yep. So a modified Hensley or a modified, Hensley or our type of conjecture, Hensley or our type of conjecture is that if delta exceeds the max of these two, then D of the alphabet contains every sufficiently large
What does the
number.
max of these two mean? You mean just the 0.8?
0.8.
0.8. Yeah. I don't remember. I'm doing this
Oh,
from
okay,
memory.
okay.
Okay, so there could be just a purely Archimedean obstruction because the purely Archimedean implies local.
Wait, so what did your student do? They proved that these are the,
Maximal, but whatever that means.
Yes, if something has a local obstruction,
then this is the highest dimension.
then it's
you can have?
contained in one of these two sequences.
Well, that's-
In order to have a local obstruction, you have to be in one of these two alphabets.
Oh, okay, so the conjecture, okay, so I see what happened. So in other words.
It's a great
they-
theorem.
There are two ways.
There are two
One,
ways.
To have local obstruction.
Yes, yes, to be a subset of this alphabet or to be a subset of that alphabet.
Very content. Yeah, I wouldn't.
And then, so what this is saying, right, is that Hensley's conjecture, this is how you would repair, well, maybe.
This is one option to repair
It
Hensley's
eliminates
conjecture.
Your counterexample.
If you like, yes.
Yeah, okay.
Yeah, is to say that if the dimension is sufficiently large, like 0.8 instead of a half, then you get every sufficiently large number. I think our conjecture is better because
They're the
it,
same, right? They're
it,
the same thing.
well, this one says more because that one doesn't say anything if you're less than
Right.
0.8 or whatever, if you're less than 0.6.
Then what happens?
Well, we do believe that every number that's 0, 1, or 2 mod 4 will occur.
So I guess your conjecture implies.
Our conjecture implies the other one. But if you don't want to talk about local obstructions, fine, use the other one. At the cost of saying less.
Has anybody worked on the bottom problem, the bottom conjecture?
This conjecture,
Yeah,
I mean, they're all, if any of them is to be solved, they'll all be solved by the same method. Or maybe not, I don't know. Who knows how anything gets solved, right? They're open problems.
I was
So-
wondering, like, how close are we to seeing anything like this?
In the way the theory stands now, the only reason you can apply this is because of Huang's theorem about what the local obstructions are. The theorem was all go through the circle method, which is, I had an hour and 20 on the circle method that I wanted to tell you guys. So, okay, we'll push it back to next week. But We can start a little bit of it now at least, but it would catch this condition automatically thanks to Huang's work.
Wow.
So, okay. I'm still on page 1.
This was very cool. We should look up the thesis of.
Yeah, so his thesis,
To see, because thesis, people say that they're more detailed.
yes,
Than
Yeah,
maybe
as materials.
sure, I can add it to, I can add a link to it. So here it is.
No. People say the thesis is more detailed, so.
So I'll point you to where this is.
The thesis is longer, that makes it look better.
No, stop this.
Okay, we say that A has no local obstructions if the set of admissible numbers is all the integers. Okay. And if A contains 1 and 2, then there are no local obstructions. If A contains no 2 consecutive integers, if it contains 2 consecutive integers, then there are no local obstructions. If it contains, there's a whole list of things like this. Yep. And so at the end, he identifies among all alphabets which have local obstructions and do not contain 1, the alphabet of all evens has the largest Hausdorff dimension.
Yeah, so the big theorem.
Right. And then, okay, so it's not 1 mod 4, it's -1 mod 8. So
This is so weird.
it's a simple thing. So then he works out what the Hausdorff dimensions are of these alphabets. So if you go out to 201 with numbers that are only 1 mod 8, then you get above a half. Yeah, exactly. And if you take all evens, then you get to 0.7.
This is because of the algorithm you said that they exist and they can produce.
Right. This is implementing some algorithms for computing Hausdorff dimensions. So again, if you get above 0.7, then yeah.
This is very impressive.
Yeah, it's a nice thesis. It's a very nice thesis. Okay. Yeah, I guess I should fix this. So what was it? It wasn't, I just skipped it.
8 and -7.
Right. So 17, 8n minus 7. Yeah, the same thing as 8n plus 1.
Yeah.
So
Yeah.
17, 25. and
It's
so on.
just like that, so that depending which index you start at.
And what did he get here for the largest one that he looked at? 0.56. Okay, so I wasn't that far off. 0.56, and this one was I mean, this thesis was 10 years ago. Yeah, 10 years ago.
It's just incredible that he was able to put together all those lemmas to actually like settle like, oh, this is as big as you can go.
Yep. And again, it's a simple consideration of if you have 2 consecutive numbers, done. You have no local obstructions. So at least you have to have a gap. If your gap is all evens, fine. That's the best you can do.
Right.
If you don't have, if you have more than just all evens, then the best thing you can do is, and so on. There's arguments like this about getting rid of local obstructions.
Is there any reason why you could stop mod 8?
It's all there in the thesis,
Yeah,
but that's the theorem. The theorem is that these are the only obstructions.
so I have to go forever.
Right. Okay. So understanding local obstructions is easy.
Yeah. that
Understanding
was-
local obstructions is easy. It's completely done, and we know what the possible admissible conditions are
For an alphabet.
for an alphabet. Understanding if the dimension is bigger than a half is also a matter of computation. Then proving the conjecture is, well, we don't know.
That's a different.
And so all the theorems actually say, if the dimension is bigger than 1, then every sufficiently large admissible number is in DA. But the dimension is so large in the theorems that automatically admissible is automatic. And so you get every sufficient large.
And then like thinness. Did we talk about why this was the right object to work with?
Why gamma A is the right object to work with?
Oh, I mean like the definition for thinness. You know, it's like, why is this going to end up giving us the theorems we want, I guess. Yeah.
So it's more the point of view, this algebra geometric point of view, to allow us to use tools from strong approximation. Although we don't actually need the tools. It's the idea that that's what should be happening.
Oh,
That leads us to understand what the local theory, what the local obstructions should be,
So this-
and that there is a local theory.
oh, okay. So this thinness allows us to connect these, like the local theory
I mean,
to,
we didn't use that the limit goes to zero, we just use the dense algebraic in SL2Z.
Yes, that's all. That's all that the thinness is just a general definition that many problems, especially recent problems, have. It turns out are asking something about a thin set or a thin group or a thin semigroup or something. So I just wanted to put that definition into your mind so that when you see it, you understand where it's coming from. So the point of this was to say, what do we gain from looking at this semigroup?
well,
This is what we gain. That mod Q, we get the group structure, and once we have groups, now we have a whole lot of technology. So why do we gain from that as opposed to just looking at the rational? Why are we doing something seemingly non-elementary when we're starting with this elementary problem?
honestly, like the rationals, right? I mean, you just graph out dots, it's really hard to say anything,
Right,
just looking at that.
right.
So,
Okay, so in 2 minutes, let's at least begin some of the ideas of the proof,
circle
Okay.
method.
the circle method. So let's so again
Wait, the proof of what?
the proof of the density one.
Oh, okay.
Okay, so this theorem of Bourgain and myself that for dimension sufficiently large, dimension of any alphabet, but it doesn't matter since sufficiently large, I don't know, 0.99, which now has been whittled down to 0.80 or something. I don't remember what the world record is now. It's not, doesn't matter. As long as the dimension is large enough, then the number of things you get up to n over how many you should get, which now you have to modify if the dimension really is less than 1. It's not all numbers up to n, but only 3/4 of the numbers. If one of the,
Oh,
if
you
there's
mean
an
like
obstruction, if there's a local obstruction, which there isn't, and we know there isn't, because these numbers are too big. But really what the theorem says is there's a fraction here in front of n, which is the fraction of
Or you
admissibles,
converge to a different fraction.
or you converge to a different fraction, exactly. But we want to converge to 1. Okay, so to start the proof, I should just start it next time. We're at time and there's almost no reason to. So the key words will be circle method. So maybe that's where we'll pick up next time.
Not circle theorem, circle method.
Not circle theorem, circle method. Yeah, I don't know that I'll have a chance to. When you do the circle method on several different problems, you really get the sense that it's not a theorem, because every single technique for how to implement the circle method is completely different. And yet the philosophy of what you should be looking for is exactly the same. So as a bird, it looks the same, and then you come down to the frog, and then it's like nothing is familiar from one setting to another.
It's so weird.
So yeah. Okay.
I have a question.
Yes, please.
For like, oh, it's for the past one, but, so we had strong approximation today.
Yes.
Isn't strong approximation also a chaotic thing, like the
Yes.
represent or a Adelic thing?
Yes.
Okay.
So what this really means,
I see that it looks similar.
yes. So
Can you clarify the connection?
okay, so you want to look not only mod p, you want to look mod powers of p. And if this holds mod all powers of p, then actually the p-adic, so this gamma is dense in the p-adic group SL2QP
Okay.
or ZP. And then the Adelic version is that actually gamma is dense. So you have an embedding of gamma into the product over all p's, into the Adelic SL2 of the Adels, and that's dense. And they have to make sense of what that topology is and what that density means.
Okay.
And what that means is, well, again, it's about this happening for all primes, and in fact, all but finitely many primes. And the finitely many primes where this doesn't happen, it still you still get everything when you go to a high enough power. So there's a stable. There's like for small primes, just like here for the prime 2, the reduction mod gamma I didn't say how you go from, I didn't say how you go from the reduction of gamma to the reduction of D. But hopefully it's clear. If you know what the matrices are, then you know what the 1-1 entries are. And so when you take your group gamma, this with this alphabet, and you reduce mod 4, the only top left elements you'll see are 0, 1, or 2, and not 3. But when you start taking, when you look not just mod 2 squared, which is 4, but mod 2 to larger and larger powers, at that point, the reduction becomes everything that it can be. So mod 2 to the 100, the reduction will be every pre-image of a matrix whose reduction mod 4 has 0s, 1s, or 2s in that 1-1 entry, or whatever the condition on gamma is. So that's why you have Zariski density at all primes.
Okay.
Sorry, that's what this density in the Adels tells you. It actually at all primes you get density, and at almost all primes you get completely onto. Your reduction is everything.
Okay.
And at a small number of primes, it's not everything, and maybe for a small power of a small number of primes, it's not everything. But then eventually, for all larger powers, it's everything that it could be under that projection.
Okay. I think that makes enough sense.
Yeah. I realize I'm saying all of these things quickly, and there's we should have an entire course on these matters, and I'm just throwing words around.